In this video, we're going to look at numerical methods of integration. That is, we're going to approximate the value of an integral. At this point, we can differentiate anything. And that gives us a sense of competence and satisfaction. But integration is more challenging. Sometimes you'd have to use very high-powered techniques in order to integrate, and other times, no matter how much we know, we can't find an antiderivative for simple-looking functions like e to the quantity negative x squared or sine of the quantity x squared. And knowing that there's no guarantee that we can anti-differentiate can be a bit unnerving. So what we're going to do now is restore our sense of having things under control when faced with a definite integral. In addition to not always being able to find an antiderivative, sometimes we won't even have a function, and then we really need numerical methods. We're going to develop methods for approximating integrals, and we'll start with just left-hand sums and right-hand sums. So we know the definition of the definite integral as the limit of a Riemann sum. So therefore, we can approximate with a Riemann sum. We can do this by partitioning the interval from A to B into n equal pieces. So I'm going to do that. I'm going to use 3 pieces. And on each piece, we're going to approximate the height of the function. So I can use the left-hand endpoint, the right-hand endpoint, or any point in between. For now, let's use left and right-hand endpoints. On the picture on the left, I use the left-hand endpoints, and that gives us L3. And on the picture on the right, in each interval, I use the right-hand endpoints, giving us R3. So we can figure out the values for this. This function, I'm going to call this particular function f of x equals 1 plus x squared. And let's suppose we were looking from x equals 0 to x equals 4. I can use a program to do the addition for me. The addition itself is not that interesting. So here is what I got. So I've put the function in here, 0 to 4. I've used 3 rectangles, and I've taken samples at the left-hand endpoints. And we can see what the estimated area is. And as you can see from the picture and the numbers, it's too low. Well, what I can do then is see what I get if I use the right-hand endpoints. So that's over here. And looking at the right-hand endpoints, you can also see that the numbers are too big, and it's too big from the picture. It would be interesting to see where are these rectangles farthest from the actual curve. What's happening in the curve that makes them far off? So think about that. The website that I used for the pictures is an interesting one to play around with. So let me put that up for you. So here's the website, and it's a really nice one. You can put in your function, decide how many rectangles you want to use, what your endpoints are, whether you want left hand, right hand. And they give you another choice in addition to left and right hand. So I'm going to leave this up so that you can go to the website. In addition to left and right hand, they can do midpoint rules for you. So here I've put in midpoint with 3 subdivisions. And what I'd like you to try and do is answer a few questions that come up from this. So you're going to play around with the website, and I'm going to put on the next slide a few questions that you should answer. So here are some questions. In our example, the integral from 0 to 4 of f of x dx, where f of x is x squared plus 1, we saw that L3 is less than the integral, which is less than R3. For this function on 0, 4, order L10, R10, L3, R3, and the integral itself. What characteristic of the function on the interval 0 to 4 informs the order? Now, let's suppose you have a value for L3 and a value for R3. One's too small, one's too big. Probably what you'd do if somebody said, okay, so what do you think the answer is you'd average them as a reasonable guess. So the question I have for you is that going to be more or less than the value of the actual integral? And if you check out the website, you can figure that out. But what I'm really interested in is, can you explain your answer by interpreting this average, the average of the left and right hand sums, geometrically? Next, I'd like you to take a look at the website, play around, and look at R5, L5, the average of those two, the midpoint sum with 5 subdivisions, and the value of the integral. What I want to know is, what order do they come in? Which is biggest, which is smallest, and which of the 4 estimates of the integral is closest to the integral? Which is next close? Can you figure out when the midpoint rule will be bigger than the value of the integral? When it will be smaller? What about the trapezoid rule? Can you figure those things out? This is something that I'd like you to think about before class. In this part of the video, we're going to look at assessing error. An approximation is of little value until we have some information about the error involved in approximating. So for instance, suppose we say pi is approximately equal to 3. Now the exact magnitude of the error is the distance between pi and 3. So here it is, it's the absolute value of pi minus 3. That's essentially useless. Getting the exact error in terms of pi doesn't help us. However, if I said 3 is less than pi, and I also tell you that the error is going to be less than 0.2, that's useful, because then you would know that pi is trapped between 3 and 3.2. That gives us some good info. Now, I could also approximate pi by saying pi, that's about equal to 3.14. You could say that the error, well, the error is definitely less than 0.002. And pi is actually greater than 3.14, so we could say 3.14 is less than pi is less than 3.142. That's true. Now somebody else may say, oh, the error is less than 0.01. That's true too. Or the error is less than 0.005. True again. Or even the error is less than 0.0016, because it's actually 3.1415, ... So all of these are correct statements. And that sometimes makes people a little uneasy because we talk about bounding in the error. And the answer to that question, give me a bound, can you give me a bound for the error, is not unique. However, it is also true that the error is less than 10, and that's a useless answer. So you want to give an answer that is a useful answer, but still, the answer is not unique. So what we're going to do is go back to the problem of approximating the integral from 0 to 4 of 1 plus x squared dx. And we're going to use the information provided by the website that I showed you to get an estimate on how big the error is. We use left-hand, right-hand sums. We use midpoint sums. We take the average of the left and the right-hand sum. So those exercises, questions, are on the next page. In this exercise, we're asking you about an integral that we actually can compute, because then we can see something about the error. And our goal in the long run is to use these methods to find something about an integral that we don't know exactly. The first question here, question number 3, asks you to go back and look at the integral from 0 to 4 of 1 plus x squared dx and its approximations by L5, R5, the average of those, and M5, the midpoint rule. And bring your observations to class. Which are the closest? Which are the furthest? Are L5 and R5 off by about the same amount? The average is better. Is it as good as M5? If not, how much worse or how much better? And then in the last problem, problem 4, you'll consider the error involved in a more general case with the function f of x that you are going to be integrating from a to b. But you should think about the example, the concrete example that you just did, to see where are ln and rn most different from f of x. What characteristic of f makes them different? So again, I'd like you to write that down and bring your thoughts to class.